So today, our topic of discussion, that is adversarial search in artificial intelligence. So already, I think resource persons have covered various topics in artificial intelligence. Particularly myself started with artificial intelligence fundamentals and introduction. There we gave a very clear picture regarding this artificial agent, how they are working, artificial agents, what is the working culture of artificial agents, and regarding various environment. Also, we discussed something regarding the propositions, first-order logic, and particularly the knowledge-based systems and what is an expert system. So next, I think we discussed regarding this probabilistic reasoning, where we told regarding this Bayes theorem as well as this Bayesian network. So today, adversarial search. I think all of you are maybe aware regarding the various searching techniques. So if I tell regarding searching techniques, as you know, that maybe immediately whatever you can recognize, maybe BFS and DFS, breadth first search and depth first search. Obviously, those two are very well-known search techniques to us. But this topic, adversarial search, obviously the search keyword is here, but again, adversary. So we have included a second keyword here also. So this is a little bit different from our general search technique. So first, how we'll proceed actually. So first, we'll try to have some recap on the searching ideas, and then slowly move to a topic on this adversarial search. So at the same time, I would like to suggest to my participants so that you can be ready with pen and paper, so that because whatever the things I will be discussing, so if immediately, if you can proceed with me, so if you can write some things in your pen and paper, then it will be much more helpful for you to understand the topic. So as I told that two things are here. So normally, what do you mean by adversarial search? Actually, this is, we say, games. So game in artificial intelligence. So then immediately that the things would come to our mind, then what is the difference between normal search technique and our adversarial search technique? As I said, adversarial searching, but this is nothing but games in artificial intelligence. So you know that once we'll proceed to the searching technique in simple search. So you have seen that in simple search, what do you do normally? So in simple searching technique, it may be that we have a search space, and our intention or our objective is to find out a solution from the search space. Here, search space mean that I mean to say that in a search space, we have some number of solutions. And here our target is to find out the best solutions or two optimal solutions from the search space. So obviously that means once we are proceeding with the searching, so what you should do. So actually, so if this is our starting state in this our searching process, and suppose so this is your goal state, okay, in our searching process, then what you should tell that here in search a solution means here we'll take a path. Okay, from this solution we may move to this, from this solution, and from these two will come to our final solution actually. So this is a path basically from the starting solution to the goal solutions. And also this path, it may consist of a number of actions, how we are proceeding from the starting solution to this goal solution. And for this, that how to implement this searching technique. For that purpose, a number of searching techniques are available. So you may be aware about that heuristic search. So one of the interesting searching technique, how to implement this searching process. So using this searching process, simply you will start. Maybe you will start with a single solution. Maybe you will start with a multiple number of solutions. So our objective is to find the optimal solution actually. And once we are searching from starting solution, we are proceeding from the starting solution to the goal solution. So in the process, we can use this evaluation function. You can say this is an objective function also. So here it will estimate the cost. Okay, once you proceed from the start node to the goal node actually. So this is our simply our normal searching techniques, whatever we follow. But once we come to this game adversary actually, now see in this searching technique, you don't have any opponent actually. So you are starting with a solution and your solution is moving forward. Okay, it is taking some series of actions and it is moving forward through the search space so that it can reach to the optimal solution. It can find the optimal solutions. So there is only one agent, no opponent is there. But suppose our situation is like that, it's not only you, along with you some enemy is there, along with you some opponent is also there. Okay, that means, so here searching process is different. Not only I am playing my actions, not only I am playing the series of steps. So along with me, some other opponents is also there. So who are opponent may be one, opponent may be multiple number. So he, she, or they are also playing with me. So what is my objective? Their objective is different from me. Suppose I can tell, okay, that my objective is to maximize their benefit. Obviously, their objective will be also to maximize their own benefit. So that means here in search, what I should say that games. So games means, okay, so adversary will be there. That means here opponent will be there. So it is also like a searching technique, but where not a single agent. Here multiple number of agents will be there or multiple number of agents will be in the process once we are searching for a solution actually. Yeah. So what we should do, so if you know, I think very good example of this game or adversarial search, I can tell that chess. So if you know that once you are playing chess, so once I am giving my move, so based on my move, my opponent is also giving the reasonable move. That means here both the players are playing simultaneously, where I am trying to maximize my benefit. At the same time, my opponent is trying to minimize my benefit as well as maximize their his or her own benefit actually. So now here, so how to find out that suppose once we are playing chess, so in a particular state, okay, in a particular state, how to find out that what is my position or how to find out what is my opponent position. So for that purpose, we can use this evaluation function. So evaluation function we can tell so that we can use to find out goodness of a solution. You know, goodness of a solution. Goodness means what is the quality of a solution. Okay, so once I am giving some move, so based on that move, I can find out what is the goodness of my solution. Similarly, we can find out what is the goodness of my opponent. So actually here, you know, what you should say that you know that what is the once we are playing some chess, then what is the board configuration? So you know, so if you know chess, that means at some particular state, what is the configuration? That means in what situation I am or what situation my opponent is. So based on that, we can find out the utility. So board configuration can give us the utility. So as that means, as I was telling, that adversarial search actually here, not a single agent. Instead of that, two or multiple number of agents are playing simultaneously or doing their actions simultaneously, where they may have some conflicting goals. And in more general, if we want to make some statement, then I should tell some statement that here that adversarial search actually. So these techniques are working, you know, as a backbone of artificial intelligence, particularly where you are working on decision making. So once you want to do some strategic decision making in the context of artificial intelligence, then you will find out adversarial search has huge importance. So simply one more statement here I should tell before proceeding. So once we will start with this adversarial search, then we are playing in a competitive environment. As you can remember in the very first day, once we are discussing regarding the fundamentals of artificial intelligence, then we discussed two things. That in an environment here we can play that it may be competitive, we can play in a competitive manner, or we can play in a cooperative manner. Environment may be competitive or it may be collaborative. But here, once we are working with this adversarial search, so here simply you are working with this competitive environment. That means I mean to say that two or more agents, artificial intelligence agents are there who have conflicting goals. So agents having conflicting goals, that means, as I mean to say, that my objective is to maximize my benefit, where my opponent objective is to maximize actually their benefit. So again, I should repeat that adversarial search, it plays a very much significant role once you are working in decision making. Particularly once you want to make some decision in uncertain environment, then you'll find out that significance of this adversarial search is huge actually. Okay. Now, let us see that once you are proceeding, I am telling repeatedly that it is one kind of searching techniques. So that before proceeding, we should know that some search algorithms or search technique terminologies. What are the search, some terminologies of the search technique? As you know, what I mean to say search. So simply searching. Searching means it may be that it is a step-by-step procedure to solve some problem. To solve some problem means what? To solve some problem means we want to get some optimal solution starting from a very much basic solutions. And here is one search space. As I said you earlier, that in a search space, we assume that a number of possible solutions may be there. And what is your objective? So your objective will be to find out or to explore the best possible solution. If it is not possible to explore the best possible solution, then we need to explore which are closer to the best possible solution in the search space. So that is our objective for any optimization techniques or any searching techniques. So we are trying to find out the solution which are pretty much closer to the best solution. And always start state will be there as well as goal state will be there. What is a start state? All of the searching process of and including this adversarial search, so they will start from a starting state. So from which state our games is getting started, that particular state we will tell as a start state. And another important thing is the goal test. Now, what is the goal test? That means goal test, so it is utility function. So it will give you that whether or not you have reached to the goal state. And once you will be proceeding with this searching technique, so it will result in a search tree. I think all of you are familiar with a tree. So, so once you're starting from the initial state, okay, starting from the initial state, then it may lead to some branches. Again, those branches may lead to some another branches. That means once you will proceed with the searching techniques, ultimately it will generate a search tree. So what we say that root of the search tree, what will be the root of the search tree? So maybe that is our initial state. Okay, from the initial state, so slowly go through the intermediate state. So we'll try to move towards the leap state, which may be our ultimate goals. Okay, now what is the path cost or what is the solution? What is the optimum solution? Path cost. So once we are proceeding from the starting node to some goal node, that means you are moving through a series of edges or you are moving through a series of paths. So what is the cumulative cost to move through all these paths? That we normally say that is the path cost. And solution. So once we are proceeding with some objective, that means, okay, from the starting solution, we need to find out the optimal solution ultimately. So, once we are discussing regarding solutions, as you know, that two kinds of solutions may be there. One is feasible solution, second one is unfeasible or non-feasible solutions. As you know, that feasible solution means not only it will satisfy all of our hard constraints, and it will try to satisfy in maximum way what are the various soft constraints, but hard constraints it need to satisfy. If you don't satisfy the hard constraints, obviously whatever the solutions we are trying to get, that solutions may not be the feasible solutions. And once you are slowly you are moving towards this optimum solutions, the optimum solution, it will have the lowest cost among solutions if you are working with this minimization function, minimization problem. But if you are working on the maximization problem, obviously, whatever the solution we are going to find, that solution will have the maximum cost among these all possible solutions. And some properties are there on this search algorithm or search problem, completeness. So when you will say that a search problem or the search algorithm is complete, if it guarantees to return a solution, if at least any solution exists for any random input. See, when you will say that a search algorithm, whatever you are working, that is a complete algorithm. A complete search algorithm, obviously, it will give you the guarantee to return one solution. I am never telling that it will return the best solution. But any of the search algorithm, once you will tell that search algorithm to be complete, so it will return one solution if at all exists. So whatever is the input you are giving, that means based on the random input. Again, I am telling, so that completeness, that means we will say a searching process to be complete. So if it returns at least one solution, I am never telling whatever the solution it is returning, that is a best solution, but at least it will return one feasible solution, okay, from whatever random inputs you are providing. So then only we will tell that search algorithm to be complete one. Another very important thing, optimality. Okay, so optimality means, so you know that normally we say that whatever the optimization techniques we will study, that none of the optimization techniques gives you the guarantee to generate or to get the best solution. Rather, all of the optimization techniques that will give you a solution which is better one. Here, better I mean to say which is very much closer to the best solution actually. So this is same thing for the searching technique. Now let us say that some few type of search algorithm. So as already I told that mainly two kind of search algorithms are there. One is the uninformed search known as blind search, and second one is the informed search known as this heuristic search algorithm. So once we will discuss regarding BFS and DFS, obviously that belongs to the uninformed, that means blind search category. And another category, it may be greedy search algorithm, it may be based first search algorithm. Okay, so all other algorithms are there, so that may belong to this informed search category. So uninformed or blind, that means no information, no knowledge regarding where is the solution, how far you are from the solution. No knowledge is there regarding the solution once you are proceeding with the searching process. So that is called the uninformed of this blind search. But once you have some specific information, specific utility information regarding the solution, that means how far you are from the search space. You should have how far you are from the optimum solutions. You should have some knowledge regarding this problem in case of informed search. But in case of uninformed search, it is blind only. That means here we need to apply some brute force technology, methodology, so to find out the best solution starting from the initial solution. So these are some examples of this uninformed or blind search: breadth first search, uniform cost, depth first. So here I will tell some ideas regarding some basic search techniques. So to set the platform, then quickly we'll move towards our target today. That as I told, that uninformed search. Uninformed search means it does not contain any domain knowledge, closeness, how much close you are to the goal of that problem. So that in that kind of information will not be provided for this uninformed or this blind search. As I mentioned earlier, you can remember, so it operates in a brute force way. You know what is brute force way? So that means you need to go through whatever the various possible paths are there to reach the solution actually. Okay. So uninformed search means, so we are searching the tree without any information regarding the search space. Okay, and we don't know actually where is the goal node. So that means we are searching blindly. Almost we are searching each and every nodes. So to reach to the goal node, once we are reaching to the goal node, obviously immediately we should stop the searching process. See, it examines each and every node of the tree until it achieves the goal node. Now you can see that how much time consuming it may be, uninformed or blind search, and how much memory it may consume. Okay, now let me come to this informed search. So informed search, as I mentioned earlier, so it will use the domain knowledge. Actually, here we feel that some guide is there. Okay, some presence of guide is there who will guide you throughout the searching process. That means each and every step, each and every state, you need to know or that how much distance you are from this particular optimum solutions. So then simply we can decide that informed search it is a much more better strategy. It can work much more efficiently than a uninformed search category. And another important thing, as you know, that informed search, that also we'll say heuristic search. I think many of you are maybe familiar with these heuristic search techniques, heuristic search. So that is a little bit different from our classical or traditional search techniques. You know, over heuristics, one more thing is there, that is called meta-heuristic search. Heuristic search is the fundamentals, then meta-heuristic search is much more improved version of this heuristic search techniques. But obviously, heuristic search techniques, so that you have much more advanced version rather than your classical or traditional searching techniques. Okay, again, one important note you should remember that heuristic means, so it may not be guarantee, it may not give the guarantee to find out the best solution. But whatever it can guarantee, obviously it will get a good solution in a reasonable amount of time. Normally, one important statement normally I will do here, that using heuristic searching techniques, so you can get the good enough solution in a fast enough manner. That means you can get the good solution. The good means I'm not never telling it is the best solution. So it is the, actually, I can tell it is the closer to the best one. And also we will get this solution in a reasonable amount of time, which is most important for us actually. If we need to wait too long time to get a best solution, that is the first case. And second case, you need to wait a reasonable amount of time to get a solution which is closer to the best one, then which one you will prefer? Obviously we'll go for the second one. So where in a reasonable amount of time you will get a solution which is very much closer to the best solution. Okay. Now let me tell you for some few things regarding one or two discerning from search category. One of the important thing is breadth first search. So I think everyone knows that regarding this breadth first search. So normally breadth first search, it works in using a FIFO queue data structure, first in, first out. So main thing behind this breadth first search is that it will start from a root node, okay, and it will expand all successors of this node at the current level before moving to the next level. That I also using some graphical context that how this breadth first search is working. So see this example. So here we are starting with this root node. So from this, if you consider this is our level 0, then from level 0, we are moving to level 1. See, starting with the root node, which is at level 0. Then slowly we are moving to the level 1. Okay, see, level 1, these two nodes are there, A and B. So when level 1 traversal is completed, then we are moving to this level 2. See, in this level 2, these four nodes are there, C, D, G, and H. So all these nodes, it will travel. That means here searching procedure is level wise actually. So a first level, second level, third level of the tree, like that it is moving. So now here you can easily assume that how much memory it can consume actually. So it requires lots of memory because it is traversing each and every level of the tree. So whatever, once you are traversing some level of a tree, obviously you need to store the relevant information. That's why it may take a huge amount of memory. Obviously, this is one of the difficulties or disadvantage with this breadth first search algorithm. And here time taking also will be more, time complexity also will be comparably more because, so it is traversing through each and every level and through each and every node. But at the same time, it has some advantages also. It will provide a solution if any solution exists in that particular search space. Because it is not leaving any node. Okay, it is not ignoring any node. Or if I say a node be a solution, so it is not ignoring any of the solution. Each and every solution it is searching in the search space. So obviously, if there is any solution, existing solution, and if we apply breadth first search, it is guaranteed. How much time it will take, that we don't know, but you will get the solution using this breadth first search technique. Now, what is DFS? So DFS is another searching technique, depth first search actually. So obviously, so it will go on depth wise, and since it will go on depth wise, so it is using stack data structure for its implementation. Depth first search normally will say this is a recursive algorithm. Okay, so that will traverse a tree or a graph data structures, if you are well known regarding the recursive solution, then easily you can understand the nature of this depth first search. So it will start at the root node. As you know, whatever solutions we are discussing, so all solution is getting started from the root node, and then in case of DFS, what is happening? So it is moving to the depth. It is not traversing the tree in a level-wise manner, rather than it is traversing the tree in a depth-wise manner. From root, it is directly coming to the leftmost node. From this leftmost, again the leftmost node. So it is simply visiting the tree in a depth-first manner. That means using the depth, not using the level. So since it is applying this depth kind of concepts, obviously it will take comparatively less memory with comparison to this breadth first search. And also at here time complexity of this DFS, it will be less than this breadth first search algorithm. So what will be the difficulty of this DFS? So if or whatever the game tree you are working, so if the tree is a very long or is a huge number of nodes are there in the tree, so maybe chances are there that sometimes it may be an infinite loop. And in this depth first search, many times what you need to do, many times you need to recount the nodes, whatever you are there in your tree. That means many nodes or many states will be simply keeping reoccurring wherever that means it may be difficult for you, and where it may for a huge tree, so it may be that complexity also may be more. And if this is the case, then there is no guarantee of finding the best solution using this depth first search. See that this is the nature of this depth first search. So starting from A, coming to the depth, leftmost, this one, then this one, then this one. You now see here. So for this enter, this is over. That means left branch of node A is over. Then it will move to the right branch. Then C, then again C to the leftmost node, then the rightmost node. So in this way, normally it will cross it. So one of the improvement of this depth first search, that is the depth limited search. That means if we can apply some restrictions on the depth, okay, up to 3 level or 4 level you can proceed, then maybe you may proceed up to that level and your searching process will be completed. So obviously it is an improved version of this depth first search. And many other searching techniques are there. So simply we are not considering all these searching techniques. Okay, so slowly we are coming to the main topic, whatever I want to focus more in this session. So as already you know that I told that informed search, it will use some heuristic value, and this heuristic value will come from this heuristic function. As already I told that informed search, that you can tell informed search as a heuristic search also. What is a heuristic function actually? So heuristic function, as you know, so it will give you the most promising path. Once you are waiting in a particular node, then you are thinking how to move to the next node or how to move to the next path from that particular state. So it will give you, if you use this heuristic function, so it will give you the most promising path from a current node. And heuristic means obviously it will give you the information that how much closer, okay, you are from this goal state. That is very much important once you are proceeding or once you are solving some problem. If you don't have any domain knowledge, that means how much you are closer or how much you are far from the goal state, then obviously it may be very much difficult to proceed with any of the real life problems. So simply in a simple sense or a simple statement, I can tell that heuristic function means that estimates how close you are from the goal state or how far you are from the goal state. Okay, now let us quickly come to that part. So these are the few examples of this heuristic search technique. It may be best first search, A star search. What is the difference from this award uninformed or blind search? Here some heuristic informations are added. Those are extra added in the searching process. Heuristic values are not added in the uninformed or blind search, but heuristic values are added in an extra manner in this informed search. So that is only the main difference between the searching process of heuristics and simply a blind search. Now let us come to the topic. I hope that now background for this session is perfectly set. Already you are quite familiar what is searching, what are the various state of searching, what are the various types of searching. Once a single agent will take place, once a single agent will do on the searching process. So that is a simple searching technique. But once multiple number of agents are there, where multiple number of agents are working simply in a competitive environment, that means searching. Once I'm searching something, it's not like that I'm alone the boss of the searching process. I don't have any enemy, so I'll control the entire world. Situation is not like that. So once you are doing on the adversarial search, working on the adversarial search, that means some opponents will be there in each and every step of this game. That's why you are telling it is a game. So here existence of opponents is there, but in simply searching process, there was no existence of the opponent. Here existence of the opponents is there, as well as I can tell which is my opponent. So their target is to minimize my benefit and their target is to maximize their own benefit. Simply they are my competitor. So we are playing, that means here searching process, we are performing in an environment where the environment is typically a competitive environment. So as you know already, you have some idea that regarding the artificial agent, I told many things in the first session. So how to tell an agent, is an intelligent agent, or when an intelligent agent may be an intelligent agent or rational agent. So here, more technically, what you need to say that multiple number of agents, okay, multiple number of agents are taking part in the searching process where their objectives are conflicting to each other. That is in the simplest sense, what is adversarial search. Simply, so this is a multi-agent environment. As I mean to say, multi-agent means here maybe 2 agents may be there, 3 agents may be there, or more than 2 agents also will be there. So, but here remember that each agent is working as an opponent of another agent, playing against each other. That point is very important to remember in this adversarial search process. So each agency, so once you are working with this adversarial search, so each agents need to consider the action of another agent and effect of that action on their performance. So see, what is the necessity of for any agent, or what is the task of any AI agent for this adversarial searching technique? So once you know that two AI agents are playing chess, then what is happening? Obviously, for the first agent, so that agent need to consider each and every action as well as effect of their action. Otherwise, they cannot take part in this adversarial search. So obviously, agents should be intelligent enough. That means they need to consider each action of another agent. Here I should make it very clear. They should consider not only each action of another agent, as well as they need to consider, they need to visualize effect of that action on his or her performance or on the agent performance. Only then the agent will be capable to participate in this adversarial search process. Now you can remember that how much difficult it is. So how, whatever the things I am telling, how these things could be implemented in a real life once multiple number of agents are operating in this adversarial searching process. So this last statement, whatever I am showing, so this is nothing but a definition of adversarial search. See, in a simple sense, what we can tell, that it is that kind of search where two or multiple number of players with the conflicting goals are trying to explore in the same search space for the solution. See, technically this is called adversarial search. It is also known as games in artificial intelligence. See, I never mean to say that all our agents are working in a different search space. You know, once you are playing chess or once you are playing tic-tac-toe, so what is the, are your search space are different or your search space are similar? So obviously we are playing on a single search space, on a similar, same search space. Multiple number of agents who are having conflicting goals, they are trying to explore the same search space for the solution. Try to make it very clear, so few technical terms I am telling, that multiple number of agents and our search space, whatever search space we are working on a same search space. Okay, and obviously we are working with the conflicting goals. If this is the case, then only we will tell those kind of search belongs to the category of this adversarial search. And adversarial search, sometimes you can tell adversarial search are nothing but those are the game in artificial intelligence. Now, okay, we are coming more, we want to focus more on the games. Now, if we say, take an example of tic-tac-toe or chess, then what kind of information, what kind of game information you should have once you are playing those games? Information, maybe initially we can categorize into two categories. One is perfect information, second one is imperfect information. Let us tell you an example that once you are playing chess, so do you have some perfect information regarding your opponent? Can you visualize the entire board? Can you visualize that what about the various actions and effects of the actions of your opponent? That is the perfect game actually. So game with perfect information in which agents can look into the complete board. Obviously, once you are playing chess, we have a perfect information. Is there anything that some moves of your opponent is unknown to you? Okay, maybe what is the effect of that particular action, that maybe it will take a much more time to think, but I can see the entire board. I can see that what are the various moves or what are the various actions my opponent is telling. So if this is the case, then the game we can tell is a perfect game. Perfect informations are there in that particular game. Now, agents will have all the informations about the game, and they can see other moves also. Obviously, in chess or checkers, obviously we can have all this information. Now, what is the imperfect game? Imperfect information. Imperfect information means where an agent don't have all the required information regarding the game. What my opponent is trying to do. What is the objective or actions of my opponent? I don't have sufficient information regarding the opponent. On an AI agent, don't have sufficient information regarding this opponent. Then that belongs to that imperfect information category. Because my AI agent, I think, is not aware about that, that what the other agent is thinking. What is going on, what will be the effect of the move of another agent. They are not aware about that. Then we can tell that game may be having some imperfect information. Battleship, once a war zone, two agents are in a war zone, then is it like that? They have some sufficient information, because each and every agent will try to hide, their action plan. So whatever they are going to do in a particular battleship, in a particular warfield, so none of the agents will reveal their actions. And obviously, none of the agents can observe the entire environment or can observe the entire scenario or can visualize anything. So this is called the imperfect information. So when we don't have sufficient information regarding the game, but obviously perfect or imperfect, whatever give the informations. So whatever our AI agent, so that our AI agent need to play so according to their own strategy. Whatever may be the information, it may be the perfect or maybe imperfect information. And another things, that another two category I told, one is the deterministic game, second one is the non-deterministic game. Deterministic game. Chess is a perfect example of deterministic game. Deterministic game, I can tell there is a strict rules, or there is some set of rules or strict some patterns are there in this particular game. There is no randomness associated in particularly chess game. Can you feel that sometimes that move of some item move of whatever you are using, so that you can take it randomly, king or queen, whatever. So can you randomly move that all these things? So we cannot do any random move here. Though they all these things they flow some strict, actually they follow some strict pattern, and chess game is entirely based on some set of predefined rules. So if this is the case, then we will tell those games belong to this deterministic games category. Now, what is non-deterministic games? Obviously, in non-deterministic games, some randomness will be associated. I should say that non-deterministic games are stochastic in nature. That means randomness will be inherent there for these non-deterministic games. Once randomness is there, that means I can tell that some factors are there. Which factors we should say, the chance factor or luck factor. So those factors may be there in these non-deterministic games. And non-deterministic games, they may have some various unpredictable event. Why it is unpredictable? So since randomness is there, so you cannot predict anything. Randomness is there. That's why it may be unpredictable event for this non-deterministic game. Obviously, once dice or these cards, so if these are parts of some game, so how you'll throw the dice, how you'll take the cards, obviously randomness will be there. They are stochastic in nature, so their actions or response is not fixed, because once I'll throw a dice, I cannot guarantee that which value will come. So simply their randomness is nature and unpredictable. We cannot predict whatever the outcome of those actions. Oh, now here I have given some examples. This you maybe know this Monopoly, poker, okay, backgammon. So of this, all these games belong to this non-deterministic game. Now see here, so chess and checkers. So both these games belongs to the deterministic category, as well as perfect informations are provided for both these two games. We know for chess and checkers what are the various rules, and obviously we can visualize the entire board for both chess and checkers. But now see, for this backgammon and monopoly, so these are non-deterministic games, as well as perfect informations are there for all these games. So battleship, tic-tac-toe. What is battleship? Battleship, see, tic-tac-toe deterministic, but imperfect informations are given there for this battleship. So if we consider something, obviously then it will be deterministic. That means, and obviously at the same time, whatever the information we have, so information belongs to this imperfect information for this battleship game. So here the summary, perfect means what? So perfect means where every participant has a perfect knowledge of the game's current state. So that is the perfect information. And what is the imperfect information? Imperfect means in one sentence I mean to say imperfect games. That means are those in which participants don't have complete knowledge of the game state. So obviously there may be some concealed information, there may be some uncertainty. Uncertainty means it may be something imprecisely known or something not precisely known, something imprecise. Informations are missing, informations are not completely defined. All these things belong to this uncertainty. Okay. And as I told again, what is deterministic games? Deterministic means the result of each and every action is entirely predetermined and foreseeable. Whatever the result in each every action, that is entirely prefixed, that is entirely predetermined. Deterministic games, there is nothing randomness or uncertainty associated with that. But in non-deterministic games, obviously this unpredictability, ambiguity, all these things are there. Now, this is another category, zero-sum game. Okay, so once it is a part of adversarial search, then obviously a zero-sum game is a huge importance one. Now, what is zero-sum game? Suppose we are playing chess. So at the end, what will happen? At the end, someone may win, someone may lose. That means if we take ultimately the utility value of both the players, it will lead to zero. If we say +5 means we have won the match and -5 means we have lost. So +5 -5 means it is zero only. So if we take sum of the utility values at any point of time, so that value will lead to zero. So that is called the zero-sum game. So obviously, zero-sum games belong to this adversarial search, which involve pure computation. That means, no, if you are playing chess in a current status, it may be you should be in a position to determine, okay, what is your, I think that utility value at this moment. So if my utility value may be -7, then who are playing as opponent with me, his or her utility value will be +7. So +7 -7, ultimately it is zero only. So simple sense, zero-sum game means agent gain on loss utility is exactly balanced by the losses or gains of utility of another agent. How much I am gaining, so that much obviously my opponent is losing. How much I am losing, so that much my opponent is gaining. So here, so here simply the scenario is like that. One player in this zero-sum game, so that will try to maximize one single value, while the other player may try to minimize it. Now remember, each move by one player in the game. So this is a technical term. So that means each move of one player that will say this. Now, ultimately, whatever the knowledge we are getting, so regarding this zero-sum game means So here, in the simplest sense, that each player's overall winning or losses are equal to 0 only. So if we take the summations of winning or loss values of two players or multiple number of players, whatever may be, so that will lead to 0. So if you take the examples of chess, so there is a very much familiar example with me. So if you take the example of chess, obviously, so if you play chess, so what will happen ultimately? So there may not be, at some point, there may not be any result. If there is no result, then again, so the value will lead to 0. And if there is someone is winning, someone is losing, again, that summation of this utility value will be leading to 0 only. Now, one most important thing, regarding this zero-sum game, so that will yield or that will formulate the concept of embedded thinking. Now, what is actually embedded thinking? Once you are playing or AI agent be a part of this adversarial search or part of this zero-sum game. Zero-sum game means nothing but this is the part of adversarial search only. So once two agents are taking part in this adversarial search, so what set should do? How, I mean to say, how it is yielding the concept of embedded thinking. So obviously, in each and every step, the AI agent need to think that what to do or how to decide the move. Okay, not only I need to think, okay, that how I need to decide the move. At the same time, I need to think that what my opponent is thinking, or what is the thought process of my opponent, what may be the possible move of my opponent as well. I should be in a position to think the thinking process of my opponent also. Only then this is a zero-sum game. Only then it will result in embedded thinking. Now see how crucial the reasoning or thinking part is coming in this, taking a place in this zero-sum game. Now this is the problem formulation. So each and every problem, there will be some initial state. Okay, that means the state from which the game will begin, and the players will be there. Now players, it may be one player particularly for this adversarial search. Obviously, the players will be two or multiple number of players. And for each and every game, some terminal test will be there. So terminal test means it will find out that game is over or not. If the game is over, so terminal test will result in true. And obviously, if the game is not over, then it will result in a false value. Another important thing is the utility value. Many times I told the term utility. What is utility? So utility function, so it will give you a numerical value regarding the game state. If you are playing chess in a particular position, so what is your utility value? That will determine that the goodness of your position, how much good position you are, or how much poor position you are in comparison with your opponent. So that will simply give utility value, give a numerical value, so that will determine the position of you and our opponent. And also we may tell that the utility function maybe we can tell this is a payoff function also. So game state, simply it will determine the game state in a particular moment. Now we'll try to focus more on these two-player games. Okay, so in these two-player games, so our main target is that we'll focus on these two-player games where our environment is fully observable. As you know, when I can tell the environment is fully observable, at the same time the environment is deterministic, zero-sum games of perfect information. So keeping all this point, we'll start with these two-player games. In these two-player games, mainly we will consider regarding two players. So one is the max and second one is the mean. Okay, so what you will find out that max and mean be two players which are taking part in this game or in this adversarial search. So target or goal of max is to maximize the benefit and target of mean is to minimize that. Now see how conflicting in nature. One will try to maximize the objective function and second one will try to minimize the objective function. And here also once we'll proceed, we will assume that here max will start the game. Okay, starting max will take part. As I told, so max always moves fast. Okay, and obviously mean with the opponent. So since this is a two-player game, and as per our assumption, what you told, so this is deterministic as well as fully observable. In which environment you are playing, that is fully deterministic as well as it is fully observable. So in two-player game, like is this searching technique, obviously it will have some initial state where the game will over, where the game will start, where the both opponents will start their game. So in chess, you know what is the initial position of both of the opponents. So this is the initial state. And also set of operators will be there, as well as terminal test will be there, as well as utility function will be there. Utility functions, as I once again I need to repeat, utility function means it is nothing but this is the evaluation function. Okay, it is the evaluation function. So it is like a heuristic function, so that it will give you the goodness of you as well as whatever be your opponent. Now let us slowly come to the critical part of this adversarial search process. So game tree is one of the important thing of this adversarial search. What is a game tree? So you can remember, suppose you are starting with a tic-tac-toe, that particular game. Okay, then you'll start from initial position. I can tell that initial position or initial state be your root node. Then from the root node, you may have some number of branches. Here I will give you some example. By that example, the concept of game tree maybe will be much more clear. So game tree. So here nodes of the tree you will work as game state. So as I told, you can remember, so we'll start with the initial state. Initial state means this is nothing but the root of that particular tree. So game be a tree where nodes of the tree are the game states. And edges, what do you mean by edge of the tree? So edges of the tree are the moves, various moves opted by the players. So once again, so just try to understand. So this is a game tree. I mean to say game tree means each and every node belongs to the states. So it belongs to the game state, and edge of the tree belongs to the moves by the various players. So game state means this is the node, and whatever the moves the various players are adopting, so that moves will recognize as the edges of that particular tree. So obviously, so game tree, it will involve initial state, action function, and the result function. Let us see the important part of this game tree. See, tic-tac-toe. Let us take the example of tic-tac-toe. So this is a very much familiar example for all of us. Now see, so this is our initial state. Okay, initial state, nothing is there. Let us say Max started its playing. Max doing cross here. Okay, then now mean will play. Now see, this is the Max is playing. Now mean will play. So mean may put the circle at any remaining positions. Based on that, again Max will play. Again mean will play. So I think at this point of time, you are finding it simple. The game is so simple. Now let us see how to represent this tic-tac-toe game using a game tree. So once we represent this particular game using a game tree, only then we will feel that what is the complexity of this game tree, or what will be the reasoning process, or how AI thinks that how to proceed with this game tree. Let us take. So initially, this is your initial state. Okay. So your Max is taking their move. So now check from Max. So in how many positions Max can put this cross? So there are 9 positions. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. And 9 rooms are there. That means initially Max may put this cross at any rooms out of these 9 rooms. So initially, what is the branching for this initial state? See the complexity. So initially, from this initial state, number of branching will be 9 only. So this initial state, that means Max can put X here, here, as well as 9 rooms are there. So out of the 9 rooms, at any room, Max can place this cross. That means from initial state, it will have a 9 branches. Now see what is the complexity will be okay here. Now from here onwards, mean will take part. Mean will put this circle. So mean will take part from this position. Now see, so for a particular node, what are the various positions that mean can play? Mean can put the circle. What are the various positions? How many positions are there? So remaining 8 positions, that 1, 2, 3, 4, 5, 6, 8. So remaining 8 positions, so out of this 8 rooms, at any rooms, mean can play. Any rooms, mean can put the circle. That means from this state only, 8 various states are generating. Now see, what is the complex kind of natures of this game tree? Try to assume it. From this particular state, again, 8 branches are coming. Initially, we have some 9 branches. Initially, we had 9 branches. Then for each of the 9 branches, see, for these states, each of the 9 branches, so again, this will come. These 8 branches will come for each of the 9 branches. Because here, this 1, 2, 3, 4, 5, 6, 1, 8. So here 8 rooms are empty. That means mean can put the circle. So at any positions, okay, out of these 8 positions. That means from this particular state, again 8 branches may come. Are getting. So what is the complexity of this? So again, what will happen from this particular state? Once max will play, then what will happen? So that means how many rooms are empty now? This 1, 2, 3, 4, 5, 6, 7. So 7 rooms are empty here. So that means, so here from this state, again 7 branches will be there. Now see the situation. From this state, 7 child node will come. Now see. So this is from this state, if it coming 7 child node, that means from each and every state like that, 7 child node will come. Simply, slowly, so one should be proceeding, complexity of this game tree will be increasing only. So complexity of the game tree is slowly increasing. That means now see the situation. So it is a 2-player game only. Max and min, they are playing their game tic-tac-toe. But here again, what is the complexity of the game tree? How many possible states we need to think about it? How many possible states we need to evaluate to complete this example actually? So if this is a part of the chess, so we cannot believe that. So what will be the various number of branches actually? So that's why normally it is told that this adversarial search process is very much difficult to implement. Now see here, what will be the complexity for this particular very simple problem we are discussing, that is the tic-tac-toe problem. But again, tic-tac-toe problem, we are finding how much complex it is. How much nodes we need to explore actually. We cannot think it beyond of our imagination if it is a part of a chess. How much possible states we need to think, so that once some AI agent is playing, that how much states AI agent need to explore, and at the same time the AI agent need to remember this each and every states. So what is the difficult kind of natures for an AI agent once you are playing this tic-tac-toe chess game? Now let us say, so here I have shown some utility measurement actually. Let us assume, so this is the terminal state. Okay, so if max wins the match, then we will give it is 1. And if means win the match, we will give you -1. Obviously, -1 plus 1, that will lead to 0 only. So here at this position, no one have won the match. That means what is the utility value? Obviously, utility value is 0 only. Here max, this mean has won the match. So we are giving it -1. Here max has won the match. So here we will give max to +1. Now, how to define these utility functions for this adversarial search process? What are the various examples of utility functions? It is not like that, whatever the way I am telling, only one utility function is existing there. So number of ways may be there, how we can compute, how we can compute or calculate this utility function. So here assume this tic-tac-toe, assume this max is using this cross X. So here whatever you are writing, just check it here. So here initially you are giving something. If n wins the match, then it is max infinity, minus infinity. What else? See the else part. Else, number of rows. Here number of rows, columns and diagonals available to max, and number of rows, columns and diagonals available to mean. So initially number of rows, columns and diagonals available to max minus the number of rows, columns and diagonals available to mean. So that may be one example for this utility function. Now see, usually you can compute here from this example actually. So how many number of rows, columns, and diagonals are available to max? See this example. How many number of first example? How many number of rows, columns, and diagonals are available to max? See, how many number of rows, columns, and diagonals? This is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. So that's why it is written here, it is 6. Similarly, here you can find out that how many rows, columns, or diagonals are available for mean. Yeah, whatever to understand this point. Yeah. Similarly, you can find out that for mean, how many rows, columns, and diagonals are available actually. This is mean, just check. This is 1, 2, 1, 2, 3, and 4. So for mean, it is 4 available. So in this, here also you can find out the utility function 6 minus 4 equal to 2. So simply, this is a way to find out the utility function once we are working with this adversarial search process. So here another example I have given. So just check it in this example for max. So this is 1, 2, okay, this is 3, this is 4. So max, so that means number of rows, columns, and diagonals, it is 4. Now how about it for mean? Let us check what is for mean. So this is 1, this is 2, okay, so this is 3. So for mean only 3. That means here it is utility function means 4 minus 3, so this is equal to 1. So now I hope you are getting that. So this is an example of utility functions for this tic-tac-toe game, whatever you are trying to compute. So utility functions, for various games, you can formulate various utility functions. So this is another utility function. So there we are showing for this chess game. So assume max is white. Now see. So these are the various pieces, as you know, this pawn, knight, bishop, rook, queen. So many things are there. So suppose all these things you are giving some values. As you know, values means significance only. Pawn, that means 1, knight, significance 1, bishop equal to knight, rook, okay, 5, queen, most significant. So here let us assume W means sum of the values of white pieces, B means sum of the values of the black pieces. So if you consider this utility function also, W minus B by W plus B. So obviously this value will range between +1 and -1. See here how we can compute the utility function for this particular game actually. Sum of the value of white pieces. So W means sum of the values of the white pieces, and B means sum of the values of the black pieces. At in a particular instant and a particular state of the game, because you may not have all these items, all these things you may not have. You may be missing some pawn, you may be missing some knight, you may be missing maybe your rook. So that means at a particular instance, okay, so what is the utility value of this particular game? So that can be determined whatever the pieces you have, your opponent have right now on this board. By that, you can find out the utility values. And this is another example of finding the utility values for this adversarial search. Here, what you can do, the previous function simply we are finding the same weight to a particular piece regardless of its position on the board. So if you see since I know chess very well, that's why I often love to give this example of chess only. So it may be someone, if you are not familiar with this chess game, so my examples obviously are going to be very tough for you actually. But here we are assuming that all of you know at least having some ideas regarding this chess game. So so once you are finding the utility function, so should we feel that all of the pieces having some different weights, or we need to give some importance that what is the positions of those pieces? I hope that you will agree with me that no, it is not only the weights or significance of the pieces, but at the same time we need to consider that exactly at which positions we are placing the pieces, because positions of the pieces are very much important for any adversarial search or any game like chess. So if this is the case, we want to give some highlight on the positions also, regardless on that particular pieces, then we can modify our utility function in this manner. Piece 1 value into x1, that is positions here, squares x my mean, I mean to say squares of the ith piece set x. That means position of these various pieces. That is also very much important once you are finding this utility function for this problem kind chess. Now, once again, here I will love to show you this tic-tac-toe game trick. See, in a glance, what is the situation in tic-tac-toe game trick? See, so this is our initial state. Max will play. Max will put x, see, cross, and Min will put this circle. So that means initially check 1, 2, 3, 4, 5, 6, 7, 8, 9. If this is the root node, see from the root node, how many branches we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Because 9 rooms are there. Na? So Max can play moves at any rooms. Max can give his or her move at any room. That means 9 branches will come. Now see, suppose Max has given in this his or her move at this position. Based on that, Min will play. Now see here. Now how many branches of Min will be there? Obviously, from this particular state, you may generate 8 branches. From this particular state, you may generate 8 branches actually. Because Min will play in 8 rooms. 1, 2, 3, 4, 5, 6, 7, 8. Min can give his or her move at any room out of this available 8 rooms. That means 8 branches will be there. Suppose Min has also given the move. Then it is turn for the Max. Now see from here. How many rooms are there? 1, 2, 3, 4, 5, 6, 7. That means from this node, again 7 different branches will come. From this particular node, again 7 different branches will come. So now see, imagine what the facts are going on. So for each and every nodes here, how many 7 nodes are there? And here each and every branches, so 8 branches was coming. Each and every node. Here each and every node, 7 branches are coming. From here each and every node, 6 branches will come. Can you imagine that what is the size or depth of the tree? And once we'll play the tic-tac-toe game, the AI agent will take part. Now can you imagine how many nodes that agent need to traverse to take some decision? We are thinking it's a very much easier one, but once it's a part of this AI agent, obviously it is going to be very much complex one. Because now AI agent need to go through each and every state, okay, to find out the optimal move. So how much complex it is to go through each and every state to find out this optimal move. Let us formulate some algorithm for this particular games, whatever you are discussing. That is the max min or simply minimax algorithm for artificial intelligence. Now, what is minimax algorithm? So minimax algorithm means so that is a recursive or backtracking algorithm which is used in decision making and game theory. So, okay, we'll go through this minimax algorithm. It is a very much significant or huge important algorithm in any of the game theoretical approaches. So here in this minimax algorithm, we will assume 2 players are playing the game. One is called max and second one is called min. 2 players, max players and min players. So they are playing the game. Okay, so max, as I was telling, so a max player, so see, one player max is trying to maximize the benefit. Obviously, min is trying to minimize the score. Target of max to maximize the score. Target of min to minimize the score. And that means here both are playing opponent and in a competitive environment. Opponent to each other. Max will select the maximized value. Min will select the minimized value. So this minimax algorithm that performed as a depth first algorithm. Okay, let us proceed with this minimax algorithm. Let us see what is the working culture or working idea of this minimax algorithm. See, so this is the minimax algorithm. So this is the terminal nodes and all these utility values are given in these terminal nodes. So as initially told that whatever we will do, max will initiate the game, then min will come into picture. Okay, so here, so this is the terminal nodes values are there. So here, what will be the next step? So that means max. So here in this level, max is playing. Max is playing means here max will take the maximum value from here. So out of -1 and 4, value will be 4. Out of 2 and 6, value will be 6. 3 and -5, -3. Out of 0 and 7, the value will be 7. Since maximizer is taking part here. So then it will be the turn for minimizer. So then minimizer, how it will play? So minimizer, it will take the minimum value. So between 4 and 6, so it will take minimum value. Check. It will take 4, -3 and 7, it will take -3. So once the turn of minimizer is over, again maximizer will take place. Okay, then maximizer, what it will do? So for see the important situation. So which is the optimal path? Just check this is the path. For this path it will take. See. Check how actually we are getting the result. How we are getting the result as 4, and which path they are taking to get the result as 4. So this is the working culture or working thoughts behind this minimax algorithm. Obviously, the minimax algorithm is complete because it will definitely find a solution if it exists in the finite search space. It is optimal. Both components are playing optimally. I will show you some example later that if some component in a minimax algorithm is not playing optimally, then what will happen? Here we are assuming that both of the opponents are playing optimally. But that is also the case if some of the opponents are playing suboptimally, then what will happen? That case will come. I'll tell at the right time. Now see, what is the time complexity for this minimax algorithm? Order of b to the power m, where b be the branching factor, m be the depth of this tree. Order of b to the power m, b be the branching factor, m be the depth of the tree. So once you are playing chess, what is the branching factor? Typically, it is 35 or 36. That may be the branching factor. What will be the depth? Normally, depth may mean how many moves you are giving. Depth may be 40 to 100. Now, can you imagine what is the complexity of this searching process? So once you are playing chess kind of game, order of 36 to the power 100. I cannot imagine actually. Order of 36 to the power 100, what is the value actually? And obviously, space complexity will be order of b into m. Now, if this is the case for time complexity, then how, I don't know that, then how this adversarial search will complete a game? How will get some result by implementing the adversarial search? Do you feel it is okay? Or we need to do some modifications using this minimax algorithm? Simply game like chess, it is giving that kind of difficulty. In tic-tac-toe, it may be branching factor, you can consider 9. Okay, that depth also you can consider 1, 2, 3. That means 10 or 20. Not 10 or 20, maximum 15 it may be. So that means now once the situation is complex, the game is complex, then what is the branching? What is the time complexity? That means it will take a huge amount of time. So that is, I think that is not correct. From fundamentally, minimax algorithm is okay, but here you need to do something. As you know that minimax algorithm, so it is traversing almost all the nodes as we have seen in the searching process. It may be necessary, but it will be searching the nodes. But if you can find out some process wherever the nodes are not necessary, if we can ignore the nodes, if you can restrict us to searching from the nodes or branches, that maybe we can tell, okay, that maybe then time complexity a little bit we can reduce. Actually, that should be our objective for this minimax algorithm. See, here a few questions I raised. That as yes, complete, yes, okay, all these things are okay only. But here that question I asked earlier that yes, optimal, yes, against an optimal component. Can it be beaten by an opponent who is playing suboptimally? So two opponents are there. One is playing optimally, second one is playing suboptimally. Then what is your thought? Who is playing optimally? And suppose first one is playing optimally, second one is playing suboptimally. What do you mean by suboptimally? Not doing the moves as per the rules and regulations. One is playing optimally, second one is playing suboptimally. So what is your thought? So who is playing suboptimally? Those who is playing optimally, can he or she be beaten by the opponent who is playing suboptimally? It can be never beaten actually. What you should say, what will be the result? Surprisingly, the player who is playing optimally, and if the opponent is playing suboptimally, suppose initially both are playing optimally, result is 4. Then if the opponent who is playing suboptimally, then the result or the outcome will be at least higher, at least better than the previous one. So that means here we can conclude that no, that who is playing optimally, he or she cannot be beaten by the opponent who is playing suboptimally. Rather, the outcome will be much more better than the previous outcome where both the opponents were playing optimally. So this is a thought process only. If you can think about it only, then we will get it. Now let us quickly come to this. This is our minimax algorithm. So as I told, that you need to generate the whole game tree to the leaves, apply the utility function to the leaves, back up the values from leaves, forward to the root. As you have seen, max node computes max of its child nodes, min node computes mean of its child nodes. When the value reaches the root, choose max value and the corresponding node. Whatever I have shown here, that exactly the same thing. Here I have written in terms of simply algorithmic sense. So this is the minimax algorithm, how it is working. So here, they search the game tree in DFS manner to find the minimax algorithm. Simply, it will search the game tree in a DFS manner to find the value of that root actually. So minimax algorithm also, it will be like this, similar manner. Now, what is the limitation of this minimax algorithm? So main drawback of the minimax algorithm that it will be very slow. It will get very slow for the complex games like chess due to the branch factor. It is a huge branching factor, and the player has lots of choices to decide. B to the power m, huge branching factor, lots of choices to decide. Which choice, which move the player will play. So based on the concept, actually, so researchers thought about this alpha-beta pruning concept. Now, what is alpha-beta pruning concept? Limitation of minimax algorithm regarding the time complexity can be improved using this alpha-beta pruning. That means we'll discard the nodes, we'll discard the branches which are not relevant to us. Okay, no need to traverse each and everything. So simply we'll prune some branches where result will be similar to the minimax algorithm by pruning that branches also. See the situation. Some branches will prune, some nodes will prune. Prune means we'll discard, we'll remove. But again, what are the results you are getting by applying the minimax algorithm? Here, the similar result you will get after pruning the node itself. Obviously, that will reduce your time complexity. So that is the main necessity of this alpha-beta pruning. Alpha-beta pruning, this is the modified version of this minimax algorithm. Very much important one in the context of this artificial intelligence. Okay, as you have seen, minimax search algorithm, that number of games has to examine are exponential to the depth of that tree. Very much difficult, dangerous things. Okay, so that means if your game states are simply growing, that means your problem complexity will be growing exponentially. So that's why you need this alpha-beta pruning. Here, alpha-beta pruning means it is a technique by which, without checking each and every nodes of the game tree, we can compute the correct minimax decision. This is called pruning. Are you getting? Pruning, no need to check each and every branches, each and every node of the game tree. Again, you will get some solution, which is very much similar to the minimax algorithm. Obviously, we'll go for this alpha-beta pruning. So here two parameters are involved. One is alpha, second one is beta. So these are only determining that which branches or which nodes to be pruned, which nodes is not to be pruned. Okay, that's why it is called alpha-beta pruning, based on the meaning of alpha and beta. It is also called this alpha-beta algorithm. Now let us come in detail. What is alpha-beta pruning? This is the most difficult part of this adversarial search process. Try to understand it better manner. Alpha-beta pruning can be applied at any depth of the tree, and sometimes it's not only prune the tree, but also tree leaves, also the entire subtree. I'll show you the examples, then maybe it will be much more clear. We want to discard, we want to prune, we want to ignore some nodes, not only nodes, sometimes entire branches also can be pruned or can be ignored, using the concept of this alpha beta pruning. So here two parameters are there. One is alpha and second one is beta. So alpha is associated with the max and beta is associated with the mean. So best choice, highest value we have found so far. Okay, in the maximizer, that means max is associated with alpha is associated with max, beta is associated with mean. So initial value of alpha will consider minus infinity, initial value of beta, which is associated with mean, will consider as plus infinity. Because minimizer, the objective is to minimize, so that's why initially starting with plus infinity. Maximizer alpha, objective is to maximize. So that's why initially starting with initial value minus infinity, very less value actually. Okay. See, the main idea of this alpha beta pruning, it removes all the nodes which are not really affecting the final decision, but the algorithm making slow. See the situation here. In alpha beta pruning, we are only going to remove those nodes or those subtrees, okay, which are not taking part in the final decision, but simply they are making the algorithm slower. Only those things we need to prune out. Ultimately, algorithm will be faster. If you use alpha beta pruning, you may get order of this b to the power m by 2. B is the branching factor, m is the depth of the tree. Earlier, using minimax algorithm, your time complexity was order of b to the power n. If somehow using alpha beta pruning, you can come from alpha order of b to the power m to order of b to the power n by 2, obviously that is a huge significance. Simply you are cutting down your time complexity by half. Okay, now some key things you need to remember regarding this alpha beta pruning. Here, actually, the max player will update the value of alpha. Remember it. Mean player will only update the value of beta. Max, since I told earlier also, so that max is alpha is associated with max, beta is associated with mean. That means max will update the value of alpha. Mean will update the value of beta. Don't make it confused. Max associated with alpha, mean associated with beta. Okay, one more important thing. While backtracking the tree, node values will be passed to upper nodes. Alpha beta value will be coming down. We'll see. Once I'll show you the example, you will get it. Alpha beta value will be coming towards the down of the tree, bottom of the tree. But node values will be forwarded to the top of that tree. That thing you need to remember. Node values will be passing to the upper side, upper nodes, and alpha beta values will be passing to the lower nodes. See, we only pass alpha beta values to the child node. That thing we need to remember to proceed with this alpha beta pruning. Now see, this is the working idea of this alpha beta pruning, which is the most interesting as well as most difficult also. Now, so let me take some water. See, what is the working thought of this alpha beta pruning? See, so at the first step, see what it will do. Just check it very clearly. So max player will start first move from node A. So it will be as you have seen that if any of the game tree. So this is our root node. That means this is our starting node. And as you know that starting node, what we have considered initial value for alpha, you can remember minus infinity. Initial value of beta, we consider it as plus infinity. Alpha minus infinity, beta plus infinity. Initial node, and this is our initialized value for alpha and beta. Again, I told that why we considered alpha value as minus infinity and beta value as plus infinity. So during the process, this value of alpha beta, see, that will be passed down that will be moving down to node B. Remember, alpha beta value will be moving down, as well as node values will be moving up. So alpha beta values will be moving down to node B. So node B, that means alpha equal to this, beta equal to this. So from here, it will be moving to this node B, alpha minus infinity, beta infinity. From node B, again, it will be moving towards node D. This is a DFS only. Alpha equal to minus infinity, beta equal to plus infinity. Now see. DFS only, na? So, we are at this, we are now particularly now at this moment. Okay. Then what will happen here? Just let me be see. Just check it here. So we are now at node D. Now you have seen how I have moved down to node D. So here, see, just a minute. Now see. So here the value of alpha C will be calculated as its term for max. As you have seen, as I told earlier, alpha is associated with max, beta is associated with mean. So now you can remember in this particular level, okay, in this particular level, so which is working? Max is working. As I told, initially max will work, start functioning, then mean, then again max. And these are our terminal node values, utility values. Okay, so at this level, max is working. Okay, so at this level, one max is working. See, the value of alpha is compared firstly with 2. This alpha is max only. So this value first will compare with 2. Okay, 2 and alpha was minus infinity. So 2, then this will compare at 3. See, first alpha will be comparing with 2. Next, this alpha will be comparing with 3. So since 3 is more than 2, because max will try to maximize its value. So which values are available? 2 and 3, these two values are available. So max will try to maximize its benefit. That means between 2 and 3, you will consider 3 value. So we'll update alpha as 3. Try to get it. Alpha is compared first with 2, then 3. And so max of 2, 3 equal to 3. So it will be updated to 3. So at this particular point of time, alpha will be 3, beta will be infinity. And what will be the node value for D? So between 2 and 3, which is maximum? Because max is working in this level, so it will select maximum value between 2 and 3. So 3 is maximum. So that means D will be 3. Okay, so D will be 3. So up to this point, it is okay. Next, what I told? I told that alpha beta value will be moving down. I told node values will be moving up. So since these 3, so at the next step, so these 3 will be copied to B. Okay, so next step, backtracking will take place. So that means in node B, so in this node B, what will happen? The value of beta will change. See, in this level, who is working? Check. In this level, mean is working. In this level, mean is working. Okay, and this node value D, node value of D was 3. So this value we are copying to node B. Since node value is forwarding upwards, alpha beta moving downwards, node value is moving upwards. So here node value will be 3. Since D was 3, we are keeping up backward. So node value of B is now 3. And here at this moment, what was the value of initially alpha and beta? You can remember. Alpha was minus infinity. What was beta? Beta was plus infinity only. Check it here. I didn't write it in here. Alpha was minus infinity. Alpha was minus infinity and beta was plus infinity only at this particular node B. Okay. So then in this node, which player will take part? Mean will take part. Which is associated with mean? Beta is associated with mean. So beta value will be updated to 3. Initially, what was the beta value? Beta value was infinity. So infinity and 3, which is minimum? Obviously 3 is minimum. So beta value is changing to 3. So that's why we have written here. Where the node value of beta will change. Now beta was plus infinity, we will compare with the available subsequent node value. That is minimum of infinity and 3 minimum. Hence here, at this point of time, alpha will be plus minus infinity, beta will be 3. Okay, up to this point it is clear. Next, what it will do? In the next point, so up to this point now it is clear. So in the next point, what it will do? Now see, so this is a DFS, depth first search. So that means now this alpha beta value, so it will be passing to this node E. So here alpha was minus infinity and beta equal to 3. DFS. So alpha beta value will be passing to node E. Node alpha equal to infinity, minus infinity, beta equal to 3. As I told you, can remember, alpha beta value will be passing down. Then again, this level is for max. That means max will participate here. So let's see here. So initially, so alpha will be compared with 5. What was the alpha value? Minus infinity. It will be compared with 5. So we can replace this alpha by 5 at this moment. Because 5 and minus infinity, which is more? 5 is more. Check at this point. Current value will be compared with 5. So max of this equal to 5. So here alpha we are making 5. Are you getting how I am making alpha equal to 5? So at this moment, alpha is getting 5. So what is the updated value here? Alpha equal to 5, beta equal to 3. Check. Alpha equal to 5, beta equal to 3. And at this point, alpha greater than equal to beta. You know, if this is the case, alpha greater than equal to beta, then we need to prune the right successor. See. Since at this point alpha greater than beta, then we can prune this node. So a right successor of P will be pruned and the algorithm will not traverse to it. The value at node E will be 5. See, this is the concept of pruning. See, by this comparison, alpha greater than equal to beta or not. At this moment, we are finding alpha is greater than equal to beta. So we are pruning this particular node. That means your algorithm will not traverse to this node. Are you getting the point? Now, so what will be the value of this node E? Obviously, the value of node E will be 5. You are not moving to this node 9. So this node you have visited. So this value will be copied to here. So value of node E will be 5. Okay, so now up to this point, now it is okay. Now next, where you will move? Now next check it. So here value of it is 5, it is 3. Now next, we'll come to this, come to B once again. Okay, backtracking. This is everything is over, we are coming to B. So here mean is taking part. What is the value of D? 3. What is the value of E? 5. So it will be 3 only. That means node of B will be 3 only. So these 3 backtracking is happening. So it will be 5. So that means now the value of node A will be 5. Since we are implementing the backtracking, so value of node A will be 5 at this point. Value of node A will be 5. Okay, next. Are you getting the fact what is happening here? Okay, some value node that I here. Yeah, so as I told, so algorithm backtracks from node B to node A. So at node A, the value of, so this value, node A, we are writing this value as 3. So node A value 3, that means here initially what was the value of alpha beta? Here you can assume initially alpha was minus infinity, beta was infinity. Node value is 3, this is maximizer. So that means which value will be changed? Alpha is associated with maximizer. So alpha value will be changed. That's why you have written alpha equal to 3 and beta equal to infinity. Is it clear? That's why you have written alpha equal to 3 and beta equal to infinity based on the node value. Okay, so that means alpha beta value we are getting. So now as a result, we are backtracking. That means alpha beta values now will be moving down. As you know, node values is moving up, alpha beta values are moving down. So these alpha beta values, it will be moving down to node C. So alpha beta value are moving to node C. That means in node C, alpha equal to 3, beta equal to infinity. Okay, so very good. So now it is DFS only. So that means again from this node, it will be coming to this node, node E. So here node F, alpha equal to 3, beta equal to infinity. Check these values only. This value is only passing to this node F. Okay, this value is only you are passing to node F. So at C, alpha equal to 3, beta equal to plus infinity, and the same values will be passed on this node E, node F. This is node F. Now at this node F again, same thing. First, what will happen? First, this 0. You see, it is a maximizer. That means first 0 will be comparing with alpha. Because alpha is associated with maximizer, so 0 comparing with alpha. Which is maximum? 3 is maximum. Okay, so alpha will be 3 only. Okay, leave it. Then, see, first max of 0, 3 equal to 3. Then it will be compared with the right side. What is the right child value? 1. Here, what is the alpha value? 3. Right child value? 1. Is there any changes in the alpha value? No. There is no changes in the alpha value. But is there any changes in the node value? Yes. Node value will be 1. Because node value will be maximum of these two nodes. So node value here, node value is becoming 1. Okay, so node value F now is becoming 1. So what is your next step? As you can remember, so node value will be moving, backtracking, moving upwards. So now C. So now what is the node value of C? So node value of C will be right now 1. Okay, so node value of C will be now 1. C. So now F returns the node value 1 to node C. At C, now what is happening at C? At C initially what it was there, remember it. Alpha equal to 3, beta equal to infinity. So here I am writing at node C initially, alpha was 3, beta was infinity. And we valued the copy 1 to C. Here maximizer is taking part, see, in this level, maximizer is taking part. And who is associated with maximizer? Minimizer. Beta is associated with minimizer. Beta is linked with minimizer. So what is the value of beta here? Beta was earlier infinity plus. So right now, so what is the node value of C? Node value of C equal to 1. So which is minimum? 1 and infinity. 1 is minimum. That's why beta value we are writing as 1. Just take it very clearly what we are doing. Here the value of beta will be changed. Okay, and it will be compared with 1. So minimum of infinity 1 equal to 1. So that means value of beta will be 1. Now at this moment, alpha equal to 3 and beta equal to 1. That means again we will check it. Alpha greater than equal to beta or not. Check. Alpha equal to 3, beta equal to 1. Yes, alpha is greater than equal to beta. If alpha is greater than equal to beta, then again the next child of C, okay, which is G, will be proved. That means remaining thing C, entire subtree. So that is proved. That is proved means entire subtree is getting proved. And the algorithm will not compute the entire subtree of G. Check. Here pruning occurs. Obviously, the algorithm will not compare this entire subtree is getting proved. Just check it. Here only one node was proved, but here entire subtree is getting proved. As I told you earlier, by implementing alpha beta pruning, it may be that entire subtree may be pruned, as well as one node also may be pruned. Okay. So now we see that now, now our working procedure of this alpha beta pruning is over. So now what we are getting? Now see here. So now what is the value of A now? So C. What is the value of C now? Value of C now 1. So 1 and 3. So value of A will be 3 only. See, value of A will be 3. Now see what is the path? See, now C returns to the value of 1. So here the base value of A, max of 1, 3 and 1, 3. So this is 3 and 1 equal to 3 only. Now see here. Now following is the final game tree, which is showing the nodes are computed and nodes. Now see. See how it is computing this particular path, and also it is showing that particular nodes or that particular subtree which will be never computed. That means obviously if this is the case, so some nodes or some branches are getting pruned, then obviously time complexity will be less only. Okay, so now we have completed this minimax as well as alpha beta pruning. Now, what was the ordering of this alpha beta pruning? You know, this effectiveness of this alpha beta pruning is highly dependent on the order in which each node is examined, as we have seen from the example. Okay, move order is a very much important aspect of this alpha beta pruning. How you are ordering, okay, how the nodes are ordered actually. Based on that, you can find out how many number of nodes you can prune or how many number of branches you can prune. So two cases, worst ordering and second one is the ideal ordering. Now what is happening for worst ordering? Now can you tell me that if we implement alpha beta pruning, so this kind of algorithm, so each and every cases, what may be the ordering of the various nodes, your time complexity will be order of b to the power m by 2. Can you ensure that whatever may be the ordering of the various nodes, time complexity of the alpha beta pruning in each and every cases will be order of b to the power m by 2? As you know, time complexity of minimax algorithm is order of b to the power m, and alpha beta pruning is b to the power m by 2. But we cannot ensure it actually. We cannot ensure it actually. In some cases, you know, alpha beta pruning does not prune any of the leaves of that tree and works exactly as the minimax algorithm. That means you may use alpha beta pruning, but you will find out time complexity is order of b to the power m only. It is not m by 2. It is based, you know, as I mentioned, it is dependent on the ordering of the nodes only. Okay, if the ordering of the nodes are not in that manner, then alpha beta pruning may not prune any leaves, any branches, and time complexity will be very much exactly similar as this minimax algorithm. And what will happen if this is the case? So it will consuming more time in comparison with minimax algorithm. Why? Because of this alpha beta factors. You know, each and every case you need to compare, you need to keep track alpha beta factors, you need to compare. Okay, so you know that such kind of pruning is called worst ordering. If by applying alpha beta pruning your time complexity is not reducing, and if orders of the nodes are like that, then what will happen? Your time complexity will be much more higher because of the alpha beta factors are involved as extra in comparison with this minimax algorithm. Okay, so in the obviously, so the best move occurs on the right side of the tree and time complexity is similar to that order of b to the power m. So that means the best move we will get on the right side only. What is our target? That best move, if we get on the left side, then maybe our time complexity will be less. If the best move we will get on the right side, then time complexity will be more actually. Because best move you are getting on the right side, that means what? You are traversing all the nodes only now. You are traversing all the nodes. Okay, let's see. Ideal ordering. What is ideal ordering? Ideal ordering for alpha beta pruning occurs and much more pruning happens in the tree. Best move occurs at the left side of the tree. So best move, this is the ideal case actually. Ideal ordering for alpha beta pruning occurs when lot of pruning happens in the tree and best move occurs at the left side of that tree. Okay, so we apply DFS, then it first starts the left side of that tree, and goes deep twice as minimax algorithm in the same amount of time. You know, we are applying whatever alpha beta pruning minimax, we are applying DFS only now. DFS only in the left first manner. So firstly it will go to the left and as much depth as possible. then it will come out from left and it will visit the right subtree like that. Okay, so that means the best move, so ideal pruning means best move will be there in the left side of the tree, and worst pruning means the best move we will get at the right side of the tree, like that. No pruning occurs, so you are moving to the right side of the tree. Pruning occurs, that means you are in on the left side of the tree. Now let me come to some conclusion from this adversarial search. Now, what is the conclusion we may get from this adversarial search? You have seen that today from my discussion started with the searching techniques, slowly coming to this minimax and adversarial and this alpha beta pruning, which are the main concept of this adversarial search. So it is one of the most important thing about artificial intelligence. Okay, maybe it is a game playing, or maybe it is a real world decision making. And since it's all about that how AI agents will navigate the environment, actually, AI agents are navigating in a competitive scenarios, competitive environment, then obviously it will give them all the AI agents and systematic and efficient means to navigate the complex environment, and as well as to understand the strategies of the adversaries. Like that only we can get. So that means, yeah, so there is some significance. We can tell that adversarial search has continuously evolved, see that, to address the challenges and ever charging landscape. Now, what is happening? So it application, alpha beta pruning application, it is beyond the games to areas, security, negotiation, multi-agent systems, making MC indispensable tool for strategic planning and optimal decision in dynamic environment. What I told using some example only, that okay, in that case, what will be the situation? But obviously, beyond that games, so we can apply the same concept for security purpose. Negotiation purpose, all is competition only. The negotiation means what? Is it a collaborative? It is not a collaborative part, it is a competitive part only. Okay. So making it indispensable tool for strategic planning. We are doing some strategic planning in the presence of enemies, in the presence of some opponents. We are making some decisions in a dynamic environment. As you can see that autonomous vehicle, self-driving car. So that means if two self-driving car are there, okay, then what will happen? Two self-driving car are coming face to face. Then what might happen? Okay, so for all these situations, they need to consider so much nodes, so much, I think, branches, so much leaves, and so that so much cases, so much states, then only they can decisions. That for to select one choice, how much depth they need to think about it, how much depth they need to traverse of the game tree to take one decision only. So for these kind of applications, obviously you can apply this adversarial search actually. As AI continues to advance, see, mastering adversarial search will remain crucial for developing intelligent systems capable of thriving in competitive settings. So in today, in real life environment where the competitive settings are there, obviously there will be adversarial search at the same time. Since AI is advancing, so we believe the concept whatever we are studying, so that also will have some advancement. Okay, so that if you feel that we are master in this adversarial search, then obviously we can contribute to develop some crucial intelligence systems where all the agents will be operating in this competitive environment. Also, you can think of this that we have discussed from minimax algorithm, how alpha beta pruning has, I think, successfully overcome the difficulties of this minimax algorithm. Now, can you develop much more intelligent algorithm which will work much more better manner than alpha beta pruning also? Because you have seen in the worst case, alpha beta pruning is very much similar like to the minimax algorithm. So itself there you can contribute so that we can develop some significant improvement of the alpha beta pruning also, and obviously that improved version you can apply for any other competitive environment. So we have 5 minutes only. So once again, thanks to our participants to take the headache to listen me for the last almost 2 hours. So it was a very much difficult concept to deliver, and I hope much more difficult for the participant to understand also, because one of the most depth topic of this artificial AI is particularly the adversarial search. Okay, what I was my objective before that session, at least I will make it clear that adversarial search everything to my participant, so that easily you can start with some and the research works. I have not told anything regarding the research perspectives, but this topic was so much depth and very difficult. So I tried to focus on the fundamental sides on this adversarial search. And I believe that if this concept, you have got this concept clearly, then easily you can do some fruitful research work using these adversarial search techniques. So now it's time for question answer. So if you have any quick question, I am ready to take. And as well as you note down my contact number and email ID. So in almost all the sessions I'm giving to you. So if you are, any of my participants are willing to do some collaborative works, so please feel free to drop me one email or to drop me a message. So this is as well as my WhatsApp number also. So that we can contribute combinedly to this artificial intelligence. So if you have any quick questions, obviously I'll be ready to take. Let me check the chat box. If you have, okay. Okay, no such questions are there. So thanks once again to my participants. So I'm waiting for 1 or 2 minutes. Actually, if you have any quick questions, we will take. Otherwise, simply I will hand over the sessions to our coordinator.